Welcome to Super Coding Fun Time with me, Eugene. This is a very irregularly scheduled Twitch fun time where we work coding problems that may or may not be related to chemistry, and maybe sometimes play some video games. I am Eugene DePrince. I'm an associate professor of chemistry at Florida State University, and this is my thing. And tonight I have with me friend of the show, Jay Foley, associate professor at William Patterson University. Yeah, that's what I said, right?
You said assistant.
I said associate. Well, this is being recorded, so we can go back and argue about it.
Yeah.
Anyway, Jay is my guest. He can introduce himself and tell you guys a little bit about himself.
Yeah, I'm Jay Foley, and despite Eugene trying to de-rank me, I'm an associate professor of chemistry at William Patterson University. And
hold on, there's people here. Maybe I would like someone to tell me in the chat if I said associate or assistant. I'm pretty sure I said associate.
Oliver's going to back me up.
Mm-hmm. Okay, anyway, go on.
I see one of my students already on the chat, which is great. Oliver, hey, how's it going?
How do you see who's actually in here?
Oh, maybe I don't. Never mind.
Oh, users in chat. There we go. Anyto. I don't know who Anyto is. Hey, Anyto. Okay, anyway.
How do you... Yeah.
There's a button that says users in chat. Okay, now that we've established neither of us know how Twitch works.
Yeah, it's, you know what I was looking at is recommended channels, and I see Oliver OG, who I think is one of my students, and he has tuned in the past.
Okay, well, we'll see if he shows up tonight. All right, anyway, what do you work on, and what are you going to code tonight?
Yeah, so we work on light matter interactions in a few different contexts, and one of them that Eugene and I have in common is when you need to consider light as a quantum mechanical object. And that particular one that we're interested in is called Platonic chemistry, but that's not what we're going to talk about today. The other, one other domain of light matter interactions that we're really interested in is controlling thermal radiation in materials.
For what applications? Maybe laser hair removal?
Yeah, exactly. So I'm trying to show a few applications in this first slide. That's our background right now. And this is not the first application that I ever worked on in this area, but it's really the one that captivated my imagination enough to make me want to really dedicate a ton of time to this, this kind of stuff. So this is called passive radiative cooling. This is one of the applications that you can do if you can control the thermal radiative properties of materials. And so I'm going to spend a little bit of time just talking about this scientifically, and then also talk about it as a technology before we get into the coding. So radiative cooling, or what I'll call passive radiative cooling, is something that actually happens all the time. And you may have witnessed kind of an unusual effect of it if you happen to live in an area where it's not very cloudy at nighttime. So if you often have like clear night skies, and if you have clear night skies when the temperature is cool but above freezing, you may have witnessed the freezing of water at above freezing temperature because of passive radiative cooling. So this can happen at night when it's relatively cool and the night sky is very clear. And basically what can happen is, even though the air is like above 32 Fahrenheit, the water can actually lose heat just as radiation out into the night sky and lower its temperature below the air temperature and freeze. So that's been observed for a very long time. And the question is, how can you take that phenomenon and turn it into some kind of technology? And more importantly, how can you make that phenomenon work for you during the daytime? Because it's great at nighttime when you don't have the sun beating down on the surface of the earth, but during the day you do. And so that becomes a much harder challenge. So really the application that I thought was really exciting is what's called daytime passive radiative cooling. And that's where you basically have something which net dumps heat into the universe in the form of radiation so that it cools itself down below the air temperature, even when the sun is shining. And so again, this happens. And this is a picture of an ant that does this. And this is called the Saharan sand ant. And it is covered with these very funny silvery looking hairs. And so those hairs do a few things. One thing they do is they reflect sunlight really, really well, because that's a big part of not getting hot in the sun. You cannot absorb sunlight, or you can absorb very, very little sunlight. There are two other things that are really important for daytime cooling. One I've already alluded to, you have to be really effective at radiating thermal energy out into the universe. So that's a part of it. But there's another component of warming that you have to avoid. So the sun is kind of the obvious one, but I'm curious, Eugene, if you know what the other contribution, it's another radiative contribution that can warm up the surface of the Earth during the day.
I don't know.
Or during night.
Infrared radiation emitted from all the water and CO2 in the air, in the atmosphere.
Yes, exactly. 100%.
All right.
Yeah. So basically, like, you've got kind of two sources of incoming thermal radiation, and you have one source of outgoing thermal radiation. And to actually do passive radiative cooling, your outgoing thermal radiation has to exceed the two sources of the incoming. So you got to be really reflective to the sun. That's the biggest source of incoming thermal radiation. But actually just the atmosphere has this black body glow, which occurs across a pretty broad range of infrared frequencies, and you have to reflect that as well.
Okay, so what's the deal with the hairs here?
Yeah, so the hairs are like these little, the hairs are an example of something that you can think of as like structural color, right? They are basically super, super white in the visible, and then they're super black in this particular range of the infrared. And I guess someone once asked me, well, what do these hairs look like? How do they get their structural color? And I didn't know off the top of my head. So I recently looked it up, and they actually are kind of like triangular. So they kind of look like, if you zoom in on the hair itself, like instead of being like a cylinder, it's kind of like this triangular prism, I guess. It's kind of like a windshield wiper blade. And so there's really, really strong total internal reflection, for example, of visible light.
Okay.
So that's kind of how it works.
So wait, so the hairs have nothing to do with the radiative cooling?
No, they have a lot to do with radiative cooling. Yeah. So let me try to be more concrete. What's the kind of ideal spectrum that you want to have? So this is the sun spectrum here in orange. Can you all see? Anybody see this?
I need to move it a little bit.
Let me make a pin.
There we go.
This is the sun spectrum.
Whoops. Okay, now I need to make it bigger again. How fun.
So that's the sun spectrum. So you got to be really reflective across the sun spectrum. And then this in blue down here is what we call the atmospheric transmittance spectrum. So this is kind of like the opposite of the information about the sun spectrum. So where the transmittance of the atmosphere is high, that's where the atmosphere cannot radiate. And that is also where you would like to emit.
And these little ants figured that out.
Yeah, these little ants figured that out. Well, nature figured that out. As who's that guy's name? Malcolm something.
Oh,
from
Ian Malcolm, Jurassic Park.
Ian Malcolm. Yeah,
Life,
nature found a way.
Life found a way.
Life found a way. Yeah. So you want to be really good at emitting in this region from about 8 to 14 microns. This is what we call mid-infrared for all of the uninitiated people here. And it turns out, actually, we emit a lot of these photons from our body. And anything that's about room temperature emits a lot of these photons. And so you just want to allow yourself to emit a lot of these photons, because these photons will just travel straight from your body or your rooftop or whatever out into the universe, because they will not be absorbed by the atmosphere. They won't be reflected by the atmosphere. They'll just go straight through. The transmissivity of the atmosphere in this range is really, really high. You'll also see that a little bit shorter than that, if I go to shorter wavelengths, the transmissivity is 0 of the atmosphere. So that's where the atmosphere has a really strong capacity.
I got excited. Thanks for the follow, Alteric Discourse.
Thanks, Alteric. That's where the atmosphere has a really strong capacity to glow back down on you, and also at slightly longer wavelengths, it's like 14 out to 20. So you need to be highly reflective to those wavelengths, as well as the solar wavelengths. That's the...
Don't get distracted, Jay.
I just was reading the comments.
I'll manage the chat. Don't get too distracted. Okay, Alteric Discourse is a physics guy.
I do want to hear more about how this is huge in quantum information systems, because this could be really helpful for me to know.
I think he's saying he's huge into quantum and QIS right now.
Oh, I thought that radiative cooling was huge in QIS. Okay. All right.
Well, actually, so by the way, Alteric Discourse, both Jay and I were trained as quantum chemists, so we like quantum too.
Yeah. Quantum. You just missed me saying that the other type of light I like to think about is quantum light.
Yes.
Well, maybe you missed us. I don't know if you missed us.
You can come back another time. We'll talk polaritons.
Yeah. So now the question is, okay, if you can do this, how do you actually come up with materials that do this and do it really well? And then, of course, the real question is, well, how do you actually turn this into a device that can like cool down your house? So there's a lot of different ways that you can think about doing this. And like, actually, there's companies now that just make paint, and you can just paint your house or paint your rooftop or paint roads or whatever with this paint that has all of these properties that I just mentioned, and they will cool things down. But actually,
can I interrupt?
Yeah,
I'm sorry. I just got excited because I thought of something halfway related. Jim Becker, do you remember him?
Of course, yeah.
He was here last weekend, and we were talking about, he's a solar cell engineer.
Yes.
And we were talking about like unusual applications of this type of technology. And he said there's like some super cheap material, I can't remember what it is, but it can be made into sheets of plastic, and it will emit in the, I guess, mid-IR maybe. And you like basically wrap a greenhouse in it, and so it makes the greenhouse super hot. Anyway.
Yes.
I guess that's the same. It's probably at least related to the technology you're talking about.
Yeah, definitely. Definitely related to the technology I'm talking about.
Jay, are you going to be doing Python today? Well, apparently there's a Solcore Python package you might be interested in.
Oh, I want to know. Yeah. Well, so it's maybe a perfect segue. So we have a Python package to design these materials, and we're gonna
have
code
as
up
cool a
something into
name
that
as
Python package
Solcore?
tonight. What's that?
Does it have as cool a name as Solcore?
No, it's got a cooler name than Solcore. I'm sorry, Solcore. Hey, if you're the developer of Solcore, I'm sorry. Actually, it's a super cool name and just as cool as WPTherml. But our software package is called WPTherml, and yeah.
Out of curiosity, how many slides do you have?
16.
Oh my God, we're gonna be here all night.
Just kidding. This. Let me just. So that's what we're gonna do today. I just wanted to spend a minute talking about it. And let me give you all a demo if I can get it out of my pen. Yeah. So you can design materials that do these things. This is just a demo of us using our software package to model a material that someone else designed. But in principle, we can do this. We can design new ones, and we have.
So here, yeah, Alteric Discourse, pay attention. You can use this in your presentation.
And by the way, I don't know if he's here, but
something happened to audio.
The founding developer of WPTherml is James Varner, who's pictured here. And he just tweeted out about us doing this, so hopefully he's tuned in. But he's now doing his PhD at, yes, he is. Hey, James. So he's doing his PhD at University of Rochester. And he is, I think, working with a big machine learning group. And I think that's correct. I hope that's correct.
And who's that?
Andrew White.
Oh, right. Yes.
Did I get that right, James?
James says, yep. James says, sup. James says, yep.
Awesome. Anyway, welcome, James. So here you go. So that's, see, in the time that I was introducing James, you could model a material that made its way into nature for being able to cool down a rooftop 10 degrees below ambient temperature.
Made it into nature, you mean like the publication?
Yes, that's right.
Okay. This doesn't have anything to do with the ants.
No. The article about the ants was in Science. And then the material that I will just say, which is probably apocryphal, but I'll still say it. The material that was inspired by the ants was designed by this group at Stanford, Sean Fan's group, and their paper got into Nature. And I think that really, and the name of that paper is something really simple, like, daytime radiative cooling, 10 degrees below ambient temperature or something like that. And I think that really started off this whole field of engineered materials for this kind of stuff.
Okay, so can you tell, wait, what happened to your figure? What were we just looking at?
Oh, I don't know. I was going to get to the...
I realized I have a mouse, so I can point at stuff.
Yeah. Okay. So here's how you would specify the materials. This is in the original version of WPTherml. Today we're going to be working in a development
How do you get WPTherml? Where would someone get it if they wanted to use
you
it?
can pip install it. So in fact, if you were to open up a Google Colab notebook, like, I don't know, this one, should I send a link to it?
Sure, throw it in the chat.
Warning, shared links. Okay. All right, how do I chat this? Yeah, so in Google Colab, for example, you could do...
Are you careful with your permissions? Can I go mess with your...
I'm not with my permissions.
So Alter Discourse will know it's you.
Just a little side note about me. I had to cancel 2 credit cards this week, or in the last 2 weeks, because I guess my credit card information.
You kept your passwords in Google Colab.
Yeah. So yeah, you can do this in Google Colab, pip install WPTherml.
That's cool.
Yeah. And so we've been working on a new release of WPTherml for like several months. I don't want to say exactly how many because then I'll become embarrassed. But a few months. And this is one piece that we have not implemented yet into the new version. So that's what we're going to do today. Were there things you wanted to ask me about on this slide?
Hold on, folks in the chat. Here's the link to the Google Colab where you can go just mess with it because there's no no permissions. So have fun with that. Mm-hmm. No, I was just going to ask you to explain the figures you had, and can you make the coding part bigger? Because all I see, most of your screen is the PowerPoint. Oh God.
Let me just go to Colab.
There you go. That's good. Okay, so you got different materials. What's thickness? So is there specific device architecture that's hard-coded here? We're talking about just layered structures?
Yeah, this is the thickness. So the thicknesses are given here. So this is coming from the geometry that the fan group optimized.
Okay.
So we just took.
So let me understand. The material list that's your layers, and then thickness is the thickness of each layer. Okay, I got you.
That's right. And then if you care about cooling, you really need to know the optical and thermal radiative properties from basically the, short end of the visible out into the long IR. So this is a way of specifying the shortest wavelength, the longest wavelength in the spectra that you want to compute, and how many different wavelengths in between. So typically for many applications, you only care about normal incidence or normal radiation. So radiation coming, orthogonal to the surface, to the emitting surface. But in this case, actually, we cannot do that. The angle dependent emission from the emitting surface is really important. So we need to calculate the emission at a bunch of different angles. That's what this is for. And cooling is just a flag saying that we're going to calculate radiative cooling properties. So this is just like a dictionary that we pass to the main class of WPTherml, which has now changed. This is no longer and whenever we release a new version, it will be done a slightly different way.
So this whole demo is about temperatures and thermal radiation. So is there temperature information that goes into any of this?
Yes, there is. So we can set a temperature, but there's also a default, which is like 300.
300 what, Jay? Fahrenheit?
Kelvin.
Okay.
Obviously. This is one of the things. Yeah, it's a good question. So in our manual, in our WPTherml manual, one of the things we say up front is everything is in SI units.
Except for okay. I was gonna pick on your nanometers, but that's meters.
No,
okay.
These are meters.
Yes.
Yeah, thickness list is in meters. Temperatures in Kelvin. So you can change the temperature, but there's a default. In fact, one of the things it prints, temperature not specified, proceeding with the default temperature equals 300 Kelvin.
Nice. Altered discourse. It may not be the only one, but it certainly is the easiest.
Nice.
Except, I don't know.
But yeah, and then so once that's done, then we're gonna make an instance of this multi-layer class, which is going to be called cool ML for cooling multi-layer. And that's going to have associated with it all of these different properties like the spectra, but also there are way down here somewhere, there should be performance metrics printed out. I guess I removed that, but let's see if I can get them back.
So that spectrum you're showing is some of that is the simulated spectrum from your material?
Yeah, exactly. Yeah. So and also some of the things I'm plotting are also just data that we store in WPTherml, like this datalib.am is getting the AM 1.5 spectrum of the sun. So
I don't know what that means. What's AM 1.5?
AM stands for air mass and 1.5 stands for 1.5. So this is like basically this is the sun spectrum at the surface of the Earth at some...
With very wet air.
Yeah, something like that. With normal humidity air.
Okay.
And then there's also... for higher altitudes, I think there's an AM 1.0 or something like that. No, I don't know. I honestly can't remember exactly the details, but this is basically the solar spectrum that you would want to use if you were talking about the surface of the Earth, um, somewhere in the United States
Okay.
would be reasonable.
So you're not emitting in that region. And
That's right. We're not
that's a good
emitting
thing.
or absorbing in that region.
And that's because you've picked these parameters to do that, or has this optimized your parameters in some way?
This is not optimized for parameters, but we can, in principle, optimize these parameters
You picked the
because
parameters from the paper?
we took the
The
parameters
nature
from the
paper?
paper.
Okay.
Yeah. Yep, exactly. So yeah, that's one of the capabilities that this also has is we can do optimizations. So we can actually take gradients of different like figures of merit that we'll talk about in a few minutes with respect to the thickness size. And so then we can figure out, should we make these any thicker or any thinner and change the layer thicknesses. And so that's something that we can do in this package. But yeah, I do, well, are there other questions you want to ask before I?
That I want to ask? I don't know. There could be questions from the chat. I don't see any currently. Okay,
Cool.
Proceed with your plan.
All right, so here's our plan. These are.
Can you make it full screen?
Yeah.
Or bigger? That works. Okay. That's good. It's fine. I have to duck.
So I mentioned there's one source of outgoing power. And there are two sources of incoming power. So one of the things we're going to try to do is implement a function that will calculate the outgoing source of power, which I'm going to call thermal radiated power. And this is how it's defined here. So this is the thermal emission spectrum of your material as a function of wavelength and angle, and characterized by whatever you specify is the ambient temperature.
300.
So, yeah, 300. The atmospheric radiation power, this is the radiated power coming from the atmosphere back down to your surface. And it depends on the thermal radiation of the atmosphere as a function of angle, and also depends on the absorptivity of your surface. So you need to know both of those things. And the solar radiation.
The user, need to know those things?
No, the computer program needs to know those things.
Does the computer program already know it?
The computer program computes these things.
Okay.
Yeah, exactly. Yeah, and unfortunately, that has already been implemented. At first that's already been implemented because I did that 2 days ago. This angle dependent stuff. At first I thought I would do all of it from scratch, but
that's a very bad idea.
That seemed like a terrible idea. Given that it's already taking me 40 minutes to just get to slide 3.
I know, this is crazy. And you said you have 16 slides. I hope that was a joke.
No, that was a joke. This is my last one. And then the solar radiation. This is the solar radiation. Okay. Little point of fact that we assume that there's only one angle of incidence from the sun, which I think is actually pretty reasonable. And that's like why, at least at a given instant in time, I think that's reasonable. And that's kind of why sundials work, right?
I don't know. I wasn't listening. I was reading the chat because there's an interesting question that I don't know the answer to. So how much worse are solar panels on Mars? What would make them worse? Is it a function of the temperature or whatever the transmissivity of the atmosphere there is?
I think the short answer is that the solar
distance from the sun. Okay.
The solar panels would be worse only in terms of their power out, right? Actually, their efficiency could very well be the same because the incident power is also much, much lower. So then the outcoming electrical power is lower, but proportional to the incident power. So in terms of efficiency, I think my 0th order approximation is they're the same.
But in terms of quantity of electricity produced, that would be
much worse. Yeah, so that's right. I don't know how much further away the sun is from. I mean, the sun is from Mars compared to the Earth, but there is a 1 over square root of R attenuation of solar power, right?
Okay. Matt Damon's coming on next week, and he can
Explain
this to us.
I think it's 1 over square root of R. I think that's like that's if I remember correctly, that's how a dipole emitter power the power emitted from a dipole decays with distance from the dipole. And the sun is clearly
So you're going to
not
model the sun as a single dipole?
No, it clearly is not a dipole, but if you're very far away from the sun.
Okay, I'd buy that, sure.
It's at least the sun is at least a sphere. So that's part of how a dipole emits. It has these spherical wavefronts, right? I feel like is Adam Rothman watching tonight? I'm feeling very Adam tonight.
You can absorb all of his mannerisms.
Sure. Okay.
Okay, keep going. Sorry.
We're almost there. Okay, and so just a quick. So these are the equations. These are making some of these terms a little bit more explicit. Thermal radiation is the black body spectrum multiplied by cosine of theta multiplied by the
What's
angle.
theta? The angle, the incident angle?
Yeah.
I thought we were normal.
No, so we need all angles in principle. We need all angles of emission into a hemisphere.
Okay, I buy that.
Yeah. So that's one of the things that makes this just a little bit more.
You got 2 more terms. Let's power through this.
Yeah. This is the emissivity of the thermal emission of the atmosphere, and this piece, the emissivity of the atmosphere, has this weird form, and I'm not going to pretend to explain to you why this is, but this is what we got from Shan-Hui Fan's paper, and Shan-Hui Fan is a person who knows what he is talking about, so I believe him. You take the transmissivity of the atmosphere, which we have, that's tabulated. You raise it to 1 divided by the cosine of the angle of emission, and take that whole quantity, subtract it from 1, and that's the emissivity of the atmosphere.
Bickety boom.
Mm-hmm. A couple of practical notes. Reasonable angle of incidence of sunlight is 30 degrees. Reasonable temperature of the atmosphere is about 300 Kelvin.
Where does 30 degrees come from? So this device only operates at, I don't know, 10:30 in the morning?
I think that's a good midday estimate.
Okay.
If you're a little bit north of the equator during the summer.
Moving on.
That's all I can say about that. Okay. Let's see how far we can get.
I should change my name in Zoom since I don't go by Albert. Too late.
Oh, well. So let me get my notes up. That's not good.
Okay, so are you going through more features or are you going to code something?
I'm going to code something. As soon as I get my notes up on a different screen, I'm going to code something.
The first time I did this, I had basically the whole project typed out on a different computer.
Oh, yeah.
Where do we teach? I am a professor at Florida State University, which is in Tallahassee, Florida, and the chemistry and biochemistry department. And Jay is a professor at William Patterson University in New Jersey. In the chemistry department? Or is it chemistry and biochemistry? Chemistry, okay.
Yeah, just chemistry.
And I'm on sabbatical this semester, so I'm actually not teaching, but somehow life is just as busy. Are the pioneers, is that Willie P?
Yeah, we're the pioneers.
Go Pioneers.
Yeah, awesome. Thank you, whoever said go Pioneers. Okay, so here's where we're gonna, here's our functions, which we're gonna fill in.
Hold on, I messed up the sizing. I was trying to keep your Slack off the screen, and I messed up the Discord.
And normally I would do, I should actually say put docstring here. Normally I would do a real doc string, but I think I need to kind of go somewhat fast.
Go Knowles, indeed.
So one of the things that I need to do probably first for computing the thermal radiated power is I need to make sure that I have my emissivity functions. So
but you're going to implement all that junk on the last slide.
yeah, that's right. That's the goal. Yeah, that's the goal. So I may not have my emissivity functions, but I can compute them. Oh, no. Sorry. Now I realized I need to do something else here.
This is why you're not doing it from scratch.
Yes, no. So if I think about my thermal radiated power, I basically need to get the emissivity of my structure as a function of wavelength and angle and the black body spectrum. And that is about it. And I need to take these integrals over them. Okay.
Alteric discourse, you're not from FSU, are you? Or you just wanted to push back on the pioneers?
I see. So I'm going to assume that I'm going to pass these S and P polarized emissivity arrays, theta
all right.
angle values, angle weights, and I'll try to explain in a minute why I'm going to do those, and wavelength array. Okay, and hopefully I have the ability somewhere to get the black body spectrum. Yes, I do have a black body spectrum here as an
input?
Okay, great. So I'm going to pass these as arguments. Okay. And then essentially what I'm going to do is I'm going to have let's see.
So I'm not a Python person. Why do you start your functions with an underscore?
Oh, yeah. So these functions are not, I can't remember the actual term for them, but they're not going to be like user-facing functions. These are going to be sort of, I mean, a user could call them, but these are sort of meant to be, I've already forgotten the word for them, but.
So it's like they're private or protected.
Yeah,
members.
That's right.
Okay. And they're automatically private or protected just because you put the underscore? No.
No, it's just a convention.
Huh. Okay.
Yeah. And
that's interesting. A lot of times with private variables in C++, they'll put the underscore at the end of the variable name.
Yeah. So basically, I'm going to have a couple or a handful of different angles. And then these emissivity arrays are going to be arrays. They're going to be 2D arrays. The row index will correspond to angle, and the column index will correspond to wavelength. So I'm going to do for I in range 0 num angles. I keep misspelling angles, don't I?
Is this Google Colab still? What is this?
This is actually called VS Code.
You're fancy.
Mm-hmm.
You and my students, I feel like an old person. I don't know any of these tools.
I know. I just learned about them like literally a few months ago. Okay, so what do I want to do? let me define,
Are you using tabs or spaces here?
I'm using, I don't know. I'm using the thing does it for me. Here,
How
watch.
can you not know?
I think tabs. So my thermal emission is going to be self dot black body. Oh, of course I need self here. Self dot black body spectrum.
So this is, again, I'm not a Python person. You're passing the instance of the class to a member of the class?
Yes.
That's weird, but okay.
Yeah, all of these class methods must take the self instance or whatever that thing is called. Yeah.
Okay, I believe you.
Okay. So, okay. This is the black body spectrum times cosine of the angle of incidence. And now I also need to multiply this thing by 0.5 times emissivity array P I plus emissivity S.
So what were the rows were angles, and what were the columns?
Columns are wavelength.
Wavelength. Okay.
Mm-hmm.
Okay.
All right. So that should be my thermal emission. And what I'm going to then do, so this I loop is going to be an integral, basically. So I need P rad 0. And this thing is now a spectrum. So underscore TE is a spectrum as a function of wavelength. And what I want to do is now integrate this spectrum over wavelength. And I've got this list of wavelengths here. So what I can actually do is say, what should I call the integral over thermal emission? TE int is equal to np dot trap z. And I think, if I remember correctly.
Here, I thought you were going to write out a trapezoid rule for us.
No, I'm going to do.
Isn't there something fancier than trap Z then?
Yeah, there is, but trap Z works really nice. It's fast. But you're going to get really impressed. I'm going to make sure that I'm doing. I can never remember if it's, yeah, it's YX. Okay, great. YX. Okay, awesome. Okay, so that's great. Now, here's the last thing I need to do. I need to integrate, I need to accumulate my integral over angle. So I'm going to say P rad is equal to P rad plus TE int times np dot sine of theta vowels I times theta weights I. And here is where those theta weights come from. If I can, this is in a different part of the package. So we're working in a file called thermal.py, which is collecting all of the different sort of high level thermal figures of merit, like this radiative cooling and stuff. but then the slightly lower level optical properties are calculated in em.pi. And I have a function that calculates the angle dependent absorption, transmission, and reflection. And you could ask, okay, well, what angles does it choose? And you could do like every angle between 0 and pi over 2, but actually that's, number one, more expensive than it needs to be. Yeah, it's just more expensive than it needs to be. So we did a little bit of trial and error with this Gauss-Legendre grid. So you can basically set up a Gauss-Legendre grid between 0 and pi over 2, and then pick your angles as the roots of these Gauss-Legendre polynomials, and then the weights. I can't remember actually where the weights come from, but they are related again to these Gauss-Legendre polynomials. So after we calculate the angle dependent optical quantities at something like 7 different angles, that's 7 going up to order 7,
okay,
is like as good as going up to 90.
So so you're doing your integral on a quadrature grid, and you get this is where you get the grid from.
Yeah.
What if your function is super oscillatory in theta? Does that mess up this?
Yeah, I guess that would mess it up, but most things actually are not super oscillatory in theta, and most things actually tend like towards very, very high reflectivity with large theta. So you don't, yeah, I mean, there are exceptions, I guess. There are occasionally exceptions with really oscillatory optical properties, but very.
I was just thinking from a normal integrating an arbitrary function point of view.
Yeah.
Okay, but you say that's not the case for these. Gotcha.
Yeah.
Cool.
Yes. Yeah, there we go. So we've got these angles and these weights that we could easily pass to our function. That's what I'm assuming we're doing with these theta weights and theta vowels. Okay. And I think the only other thing that I'm missing is I feel like I'm probably missing a factor of pi somewhere. Yeah, I'm missing a factor of 2 pi. So at the very end of this, I'm going to do p rad times equals np dot pi times 2 and return p rad. And I'm going to like really hope that is right. Again, depending on how long it takes us, we will try to write a unit test for this. But yeah, I think that's done.
Cool.
There we go. There's one function. One done.
And our goal are these three functions.
Mm-hmm.
I think the last time you were on here, I was remarking how jealous I am that I don't do things in Python, because this is really straightforward.
Yeah, it's super straightforward, right? Okay, next one, compute atmospheric radiated power. And I'm going to also take self.
Why don't you just copy? Is it the same arguments as the other one?
Yeah, just about. I need one more thing. I need also the atmospheric transmissivity.
Jay, it's funny. When you first told me what you would be talking about today, do you know how you described it?
No.
You said you'd be talking about radiative cooking.
Cooking?
Which I was pretty sure wasn't correct.
Yes.
That's where you crack an egg on your radiator.
Yes. So I'm going to call the atmospheric transmissivity. Okay. The other thing that's really nice about this VS Code, by the way, Eugene, is that it color codes arguments to your functions and variables based on whether or not you've used them a second time. So notice these are all like, are like dark blue, and these are like a lighter blue. These started out dark blue, and then once I use them within the function, they turn light blue. And these will turn light blue once I use them within the function.
Okay, that's interesting.
That's pretty nice. I think it's nice. Okay, what are we going to call this thing? Again, remind ourselves to put docstring here.
What's the name? What's the name of this?
PATM, I guess.
No, the name of the editor you're using.
Oh, VS Code.
VS Code.
Yeah. So we took a multi workshop over last summer called Software Package Development Best Practices.
Okay.
And this is where we learned about doing. So let me just show you a better docstring. This is a more proper docstring for a different figure of merit. And we have like a link to the equations. We have all the attributes. We have the arguments. There may be even a real, well, whatever. And so we learned about, how to write good doc strings, and we learned how to use this VS Code editor and all these like little things that turn out to be super useful. I highly recommend that workshop. It's a great workshop.
Mulsi, you said?
Yeah, Mulsi's Software Development Best Practices. I haven't looked at the Twitch stream in a while, but I wonder if Sina's here. He used to come hang out, right?
Yeah.
Where is Sina?
Python package best practices or best practices?
Yeah. I think Python package best practices.
Oh, wow. This stuff is all, there's a thing you can just look at.
Mm-hmm.
Cool. So that, here you go, chat.
So yeah, this is going to look a lot like our last one.
What's a good package to work QM problems? It depends on what you want to do. You probably want something free if you're doing it for a class. And there's a few good free packages. I am a big fan of one called Sci4. That's where we develop most of our codes. Other folks are, I think Jay's also a fan of Sci4.
I'm a huge fan of Sci4.
Sci4 is like a mix of C++ and Python. All the stuff that a user would do is on the Python side. And you can develop, here, PSI4. And I think it's scicode.org. Oops, that's not correct. Let me get you the actual link. And they actually have, you get it through GitHub or whatever. I can drop the GitHub link as well. And then I'll tell you another one after I finish doing that. So here's the GitHub link. And then there's another package called PySCF that's like 100% Python. No, it's a side question, but it's now I get to talk. Jay's been talking the whole time.
Mm-hmm.
And so here's the link for PySCF. So I don't know which one has a lower barrier to entry, but they're both good codes. You can do like, Hartree-Fock, density functional theory, couple cluster. Which are standard QM methods. All right, Jay. Now that we haven't forced you to talk the whole time, you probably were quite productive.
Nope.
Working on perturbation of hydrogen atom. Cool. There's perturbation theory stuff in all of these codes too. Yeah, what kind of a perturbation?
Hopefully a weak one.
Oh, there's only one electron.
I have a Jupyter notebook with a perturbation to the hydrogen atom that is really funny.
What's the perturbation?
The perturbation is different screening of the Coulomb potential. So this is a good model for an exciton and a nanoplatelet. There's one other difference, which is that the masses are different. So in an exciton, it's not, you don't have the proton mass and the electron mass. You have a whole mass and an electron mass, and neither are the same as they are in the hydrogen atom. But the other thing is that the like the exciton, when its wave function is localized within the nanoplatelet, experiences 1 Coulomb potential because the dielectric constant of the nanoplatelet is really high. It's like 10. So the Coulomb potential is screened a lot. And when the part of the wave function, which extends outside the nanoplatelet, experiences a much stronger Coulomb potential. So you can't actually treat this with perturbation theory, but you can try, and it works okay. But we have both a perturbation theory and a variational approach for this kind of system in the Jupyter notebook somewhere.
Well, at some point maybe you could find that, but later. Altered discourse.
Oh, I'm just going to talk about it and hang out this one line.
Who wants to watch my cursor blink some more? Altered discourse. Unfortunately, you get what you pay for here. We could just be lying to you the whole time. Just kidding.
Yes. Okay, so this is TE atmosphere, thermal emission of the atmosphere. So what have we done? This is our weird 1 over cosine theta term. This is the emissivity atmosphere. Which
Are you trying to save character space? Why can't you say over?
I don't know.
Oh, you did it twice. It was intentional. You did it twice.
Yes.
I'm
Okay.
just kidding. You can call it whatever you want.
Oh, I'm going to change it just for you. It's so particular. Okay. So that's the thermal emission of the atmosphere. Absorbed TE is equal to TE atmosphere times 0.5 times emissivity array P S plus emissivity S. Call it spectrum, and then absorbed TE is equal to NP dot trap Z, absorbed TE spectrum, length array. Just want to make sure I'm not missing any other weird angle things.
Man, if I had a nickel for every time I wrote a trapezoid rule,
I know.
I'd have a lot of nickels.
I used to do that all the time, and I used to make all of my students in phys chem do it. And then I learned about, like, I literally didn't know about trap Z until like a year ago. And I was like, why would I do that?
Do you think it's useful for your students to still learn how to actually do it?
Actually, I do think it's useful.
I agree with you.
It's useful, but then it's also this time trade-off, because I think it's useful to do it, but it depends on how much time you can spend.
So I guess for like a chemistry class, it's not your job to teach how to do a numerical integral. You want to use that tool to do chemistry or physics or whatever.
But it's yes, and I think it's just honestly, I think if I had more time in a semester, even in a chemistry class that was oriented towards teaching chemistry, I would still do this, because I actually kind of believe that showing numerical tricks like that are simple, right? And it's just, the trapezoid rule is not a hard trick. It's not a hard thing to code. It kind of demystifies things a little bit, and the more that you can kind of do that, I think over time it kind of help students absorb more of the quantitative content.
Yeah. Does this function have any? Do you have any control over? Oh, you give it an array, so that the spacing is controlled by the array. Okay, now I understand.
That's right. That's right.
Obviously. Okay.
Yeah.
Does the coordinate you're integrating over have to be spaced regularly, I guess, for this function to work?
It doesn't, actually. It doesn't have to be spaced regularly. Yeah. So it takes this entire independent
yeah, okay, that makes sense.
Independent variable axis. So yeah.
Fancy.
Mm-hmm. All right. Back to the thing at hand. Yeah, okay. P ATM plus equals absorb TE times NP dot sign theta bows I times theta weight I ATM times equals 2 times NP dot pi. Yeah. Okay. So that's our second one, hopefully.
Cool. And we're just not going to test them. We're just going to fly by.
We're going to test them all at once, I guess, because I got to go to another notebook to test them. So, and that's the part I'm a little nervous about, is the testing, for reasons I'll explain once we get there.
Okay.
Okay. Compute solar.
Everybody who's here, Jay had well, I guess if you're just joining, this is a Supercoding Fun Time with me, Eugene. And it's meant to be a place where we do fun coding programming projects in whatever language that may or may not be related to science. Jay and I are both quantum chemists, and we're both interested in light matter interaction, so that's what he's doing. Sometimes we also play video games, and Jay had promised he was going to play Punch-Out today.
Yep.
And he's just ignoring me. I'm very sad that he's actually not going to play Punch-Out. So you just need to figure out how to hook your Twitch up, your Switch up to your computer screen. Is that what it is?
Yeah, that's right. I assumed that there would be a way to directly connect the Switch to Twitch, but then I read that there is not. So that is a problem.
Well, for next time you come on, you have to get an adapter, I guess.
Yeah, I guess so. That's how it's gonna go.
I had one when I first started doing Mario speedruns. I had an adapter to record off of an NES.
Oh, nice.
So if they make them for an NES, I'm sure you can get an adapter for a Switch.
Oh my God, I think it's just gonna happen in one shot.
What?
Let me just this really quickly.
So you don't want me to distract you anymore?
No, you can distract me.
Are you going to the ACS San Diego meeting? Yes, you are. You're a moderator.
I'm going to be there virtually.
Ah, okay. Are you going to the ACS Chicago meeting?
I don't know.
It's August.
Are you?
Yeah. I can't wait. It's going to be great.
When are abstracts due for that?
I think mid-March, maybe the 14th or 15th. Alex Sokolov and Francesco Evangelista are organizing a ginormous symposium that has like 40 invited speakers.
Oh, nice.
And it's many different topics, so you should see if you fit in one.
Unless it has something to do with players, I was going to say probably not.
I think it had a dynamics aspect.
Oh, nice. Okay.
So Jay, what are you teaching this semester?
Gen Chem 1, Phys Chem 2, and Graduate Quantum.
Do you do any coding in Gen Chem or Phys Chem?
No, I don't.
In Phys Chem even?
Yes, I do. Although I'm not doing the lab in Phys Chem for the first time ever. So my adjunct is doing the coding.
Every year about this time, I think, I want to revamp how I teach graduate quantum mechanics and include more coding.
Yeah, you should.
I should, I know. What do you cover in grad quantum? What would you suggest to an undergrad prepping for a course like that? Well, first, in terms of the preparation, when I got to graduate school, wait a second, you're going to graduate school, you should come to FSU. That's number one. Then you can be a null grad, like your family. The first thing I'll say is I was grossly underprepared for PChem. Nice, okay. For graduate quantum mechanics, and everything worked out okay. So you can learn everything you need to learn in the class. But I'd say the thing that most people struggle with is just math. You need to know integrals and complex numbers and all that seemingly basic stuff. Practice your math. Yes, practice your math. Because it's really easy. It's not a math class, but some people feel like it is a math class. So anyway, in my grad quantum, Jay, you can go next. I'll leave you alone for a second. In my grad quantum, I teach from Levine, and we cover like the first, 7 or 8 chapters of Levine. And it's very similar to an undergraduate quantum class. We just do everything in more detail. So we do postulates of quantum mechanics, a bunch of model problems, particle in a box, harmonic oscillator, hydrogen atom, but we actually solve them. Whereas in the undergraduate course, you just learn the solutions. And then we do variation principle, perturbation theory, and we finish up with like practical quantum chemical methods like Hartree-Fock and second order perturbation theory, and try to like at least understand some of the expressions that show up there based on what we had learned in the rest of the class. What about you, Jay? What do you cover in yours?
So in the graduate quantum, we do actually we do Hartree-Fock and perturbation theory, and a little bit of CI, and then a little bit of polariton chemistry.
Polariton chemistry,
yeah,
useful for the average student.
Well, so we have a materials focus in our graduate program, so it is useful in the sense that in that it is a nanomaterials relevant topic. I think it's useful. Of course, I am biased. Yeah, sorry, I'm trying to.
So I actually, in the chat, I actually don't know this book. I'm looking at it now on Amazon. Quantum Mechanics: A Paradigm Approach. Yeah, I don't know. I know nothing about it. Do you like it? Altered discourse. And I guess we also do some time-dependent perturbation theory as well. Sometimes. I don't cover that every time. Which is where you like derive Fermi's golden rule, which tells you basically what an absorption spectrum would look like for a molecule. Developed by an OSU guy. Is that Ohio State or Oklahoma State? Lots of good QM-related pedagogy research coming from them. What's QMII? Oregon State. It's too many OSUs. What's QMII?
QMII.
Yeah. Oh, quantum mechanics too. I was like, quantum mechanics and information institutes? I don't know.
Oh, that's not good at all. Oh, I guess that's to be expected. Okay.
All right, so you're actually using your functions now.
I'm using the old WPTherml, and I got to remind myself of a few things. So also, can you all see my terminal right now?
Oh, I think Ken showed up. Ask a Scientist Gaming is here.
Oh, Ken, welcome. So if you can see my terminal.
You guys should all follow Ask a Scientist Gaming.
One of the things I'm going to do right now is commit some cooling functions. Testing. Okay.
Are you committing this to your main branch?
No, I'm committing it to a cooling branch. Am I still in a quote? I'm still in a quote. What's going on here? Control C.
Well, it's fine. We can't see what you're typing in. Oh, there it is.
Oh, git add.
Jay, do you teach any other graduate courses or just Grad Quantum? Grad Quantum 1? Do you have another Grad Quantum?
No, we have one grad, and I call it Grad Quantum because it's 2/3 quantum, but it's also got classical mechanics in it that my colleague David Steiner teaches. He does like some classical MD and things like that. And then we have a nanomaterials class, which I do teach, a graduate nanomaterials class that I teach. I sometimes teach like 1/3 of the graduate inorganic materials class, but I talk about lasers and solar panels and things like that, but I don't teach that very often. And we have a graduate seminar and research methods class that I also teach.
What goes into a seminar course like that?
So big part of it is seminar attendance and preparation. So like we have the students give presentations on the speakers before they arrive to like get ready for their talk. They do a pretty like extensive series of journal clubs in that class, and then they do a proposal, and then we also throw in some topics like how to write a resume or how to write a proposal or how to write a paper and a response to reviewers' comments and things like that.
No, you're wrong. That's how you respond.
That's how you respond. Okay. So, another thing I did, I ran all of our unit tests, and I haven't introduced any errors to any of the existing unit tests with the new functions. So that's good, but we haven't written unit tests for the new functions. So I need to do something really quickly so how am I going to do unit tests? So first of all, maybe I should define a unit test. So a unit test is going to run your functions against some, standard case or some case for which you know the answer, and make sure that your function gets the right answer for some case that you know. That's basically my brief synopsis of a unit test. And you want to have a unit test in principle, you want to have a unit test for every function. And the reason you want to do this is so that you and your users and your code developers are all assured that your code has not been broken in a way that changes, its goodness on the things it's supposed to do. And so whenever you're introducing new changes or additions into your code, right, once you have completed a set of changes, you should run your unit test to make sure you didn't accidentally delete something that breaks the functionality from before. Then you should create new unit tests for the things that you added to certify that those are okay. So now we have these 3 different functions. What I want to do is come up with a unit test for each of them, where basically I'm going to take some really basic structure and compute its thermal emitted power, compute the atmospheric radiation it would absorb and the solar radiation it would absorb. And where am I going to get those kinds of values to compare against? I'm going to use our old version of WPTherml, which we did, extensive benchmarking on. But I need to first of all remind myself how to get those values out. And number two, I need to come up with a structure which is simple enough that I can be convinced that they will compare fairly against the two.
So we got an answer on the perturbation that was being applied to the hydrogen atom.
Oh, awesome. What's the perturbation?
Relativistic effects, I guess spin orbit coupling or something like that. So
nice.
for hydrogen atom, it is a small perturbation. And then we're being asked our favorite interpretation of quantum field theory. I'm going to go ahead and say I do not have a favorite interpretation of quantum field theory because I know essentially nothing about quantum field theory.
No idea. Okay, so these are the three values that I
lowly chemists.
Yeah. Radiative power val. So let's print these things out.
Thank you, Brian Kulbrick, for the follow. I noticed my upload speed was like super duper slow for a second, so now there's a huge lag. Hope that doesn't negatively impact things.
Atmospheric power valve.
Oh, and I gotta find a charger, so you're on your own for a second, Jay.
Okay, I gotta talk and code at the same time. So...
Or you could just sit in silence and bleed viewers, that's fine.
I can do that too. So I'm getting these quantities from the old version of WPTherml, as I said. And one of the things which is tricky, so the sort of computational engines that we use to calculate all these quantities, right? It's not like those are variable or that they change. So you could say, well, should be really easy to compare these numbers that you're getting from the old version to the new version. One of the things that is a little tricky is to do, so the calculations that WPTherml is doing under the hood are solving electrodynamics equations, so solving Maxwell's equations for these structures. And one of the things you have to feed into Maxwell's equations are these, basically experimental or phenomenological values for each of the materials called the refractive index or the dielectric function of the material. And those typically come from experiments, and they have experimental data sets that we read from and that we interpolate. And actually, not all of the material, in fact, the vast majority of data sets that we use in the current version are different than the old version for some reason or another. I can't remember why all of them are different, why so many of them are different, but many of them are. So, even small changes in those data sets will actually lead to, differences in the results that at least a unit test will pick up as being different. They're not significant in the sense that, if the material that in the old version, the data set for glass that we were using, for example, may be slightly different than glass, now, the optical properties will not be dramatically different, but when we do a unit test, we're going to try to compare, numbers to like, I don't know, 3 or 4 or 5 decimal places. And so small changes in those experimental data sets that feed into the electrodynamics equations will actually show up in those, in that precision. And so what I'm going to do is with old WPTherml, I'm going to make a really simple structure, which is just one layer, and it's got a constant refractive index of 2.4 plus 0.2 I. So this is a weakly absorbing material with a relatively high refractive index. It's something that's totally made up. And, but I'm hoping that by doing this, I can guarantee that my electrodynamics solver is going to give me exactly the same spectrum for the old version and the new version because it's got the same geometry and the same refractive index. And then I can just test out the new equations that I implemented that use the spectra. Okay. So that's what I'm going to try to do. And so here's our reference values. And yeah, the other thing I just realized is I'm not quite done yet on this side of things. I'm not quite ready to do my unit tests. That's what I just found out. And Eugene, are you back?
Yeah, I'm here.
Okay, great. So
you're doing such a great job. I just thought I'd let you keep going.
Yeah, I got to come back to I feel like I had given myself some note somewhere like, hey, this is where you should do, this is where you should call those things. Ah, here we go. Yeah. Okay. So this is back, just to orient everybody, this is probably super confusing, right? I added these new functions in thermal.py. That's this, collection of functions that deal explicitly with these thermal applications and computing these sort of what we call high-level figures of merit, right? These are basically, you're going to take different spectra and turn them into a number. And then em.py is what generates the spectra. Okay. And so, so this is a little flag that says if I want to do cooling calculations, I'm going to compute these explicit angle spectra. And then what I'm going to do next is call this compute thermal radiative power. And look at this, it's going to tell me this is another nice thing that VS Code does for you. Do you see this, Eugene?
Yeah.
It's telling me the arguments in the order that I should put them.
Why doesn't it just do it for you?
That's a great question.
I saw this on Twitter recently. If a compiler knows you're missing a semicolon at the end of the line, why doesn't it just add the semicolon at the end of the line for you?
I don't know. Okay. So that is calling that thing, and I guess I'm going to store this to a new attribute. So so we'll call this thermal radiated power is equal to this. Is that a good name for an attribute? I guess.
For tonight's purposes, I think it's perfect.
Yeah, good enough, right? Self.atmos.
Unless you want to abbreviate it by just removing one letter from in the middle of a word.
Wait, you mean like this? Because actually that's something that before we release this to the public, I need to make sure that all of the thermals are either spelled thermal without an A or, just thermal like the package thermal.
Now I'm trying to figure out, I've never clipped text, but I would love to clip, or not text, clipped video. I'd love to clip that reaction of yours.
Yeah.
Oh, and I missed it.
Oh, man. How are we doing watching wise? Is this like really bad or?
I think it's pretty good.
I just realized this might be a little bit boring. I don't know.
I think it's great.
Okay, great. I'm feeling like it's very productive. This has been on my to-do list for so long.
It looks like there's 8 people watching. If I check on users in the chat, it looks like there's 10 people here, so I don't know which number is correct, but it's not
James
0.
there?
When Jim was here the other night, we had like 1 viewer the entire time. It was great. So we were just talking to each other.
That's great. Okay, and then I'm gonna do something else here. This is a little bit ugly, I think, what I'm about to do here.
I mean, you have self dot everywhere. It's not capable of being pretty.
I guess you're right. Self dot theta bounds angle incident angle is equal to self dot solar angle.
When you were in graduate school, did you code in Fortran or in C?
In C. I know like a very tiny bit of Fortran.
I just asked because I didn't know our PhD advisor is a Fortran person, so I didn't know if you...
Yeah.
Do you ever code in C and C++ anymore? Just Python?
I have not coded much in C or C++ in a few years, but I will. I will, for sure. With all of this Platonic quantum chemistry stuff, seems necessary.
I guess if you wanted to be fast.
Mm-hmm.
I need to come up with clever questions for you. You still run?
Yes, I do. I have not run in about a week though. I guess I ran on Saturday, but then I got kind of sick. June had some bug last week, and I was home with her most of the week. I think, yeah, Jessica and I somehow traded off a few days, but I was home with her for many days.
You don't ever go jogging with her?
No, I do. I do go jogging with her, but what I'm saying is I got sick.
Oh, you got sick from her. I got you.
Yeah. So I haven't gone running in a few days. I started feeling normal sometime between yesterday and today.
Well, thanks for coming on, even though you're barely normal.
It happens, right? Okay. That comment is going to go here. Okay. So, sorry, this block here, I had all of the emissivity spectra at my angles on my Gauss-Legendre grid from here, but there's like this one particular angle where I need absorptivity of my structure. That's at whatever the solar angle is. So I just needed to compute and grab the absorptivity at that solar angle for both S and P polarized light.
Hey, explain to me like I'm 5 what S and P polarized light is.
Yeah, so light has an electric field, which means it exerts forces on charged particles, and forces always point along a direction. So the S polarization and P polarization tells you which direction, if you've got light traveling towards a surface, it tells you which direction relative to the direction of travel and the surface is the force pointing. And can I remember what S and P the SMP convention is. No, I can't. But it's like, again, I got to make sure I'm gesticulating in the right way. Let's say that my keyboard is my surface, and this is my finger is the direction the light's traveling. Right, my force could be pointing sort of towards, towards the. Well, my thumb could be the direction of the force. That's one polarization, or I could twist my thumb 90 degrees. That could be the other polarization. That's the best I can say.
Why are they called SMP? Do you know? Does this have anything to do with why atomic orbitals are called SMP?
I don't think they do, actually, but I could be wrong about that. I could be wrong.
Okay, so SP, D, and F stand for sharp, principal, diffuse, and fundamental, as in lines from alkali metals, according to the internet. So it must be true.
Yeah.
Something tells me that's not what S and P mean in this wave context. Chat died.
Oh, that's too bad.
It's going pretty good for a while there. Have you ever run a marathon? Yes, you have, right?
I have one time. Yeah. How about you? You have.
I've run one, yeah. Do you have any horrible marathon stories? Like your body fell apart and...
Yes, I do. Give me 1 second. I gotta really focus here. Yeah, I do. Oh my gosh. No, the marathon that I ran.
Do you run Chicago or a different one?
It was in Madison, Wisconsin, and I trained like a moron. So I got injured, and then I think I got injured like a month and a half before the marathon. And I didn't decide to pull out of the marathon. I just decided to aqua train. So I was aqua jogging, and I was doing a lot of it. So I thought everything would be fine. But what I didn't really think about is the fact that aqua jogging is basically a zero impact thing. So yeah, like it's good cardio, but it is doing nothing to condition your muscles and your connective tissue for 26 miles of pounding on the pavement. And also it's cool. And the marathon was on Memorial Day when it was really hot. So I had a horrible time. I basically walked the last 8 miles or something.
Oh, that stinks.
Couldn't force myself to run anymore. And I was so hot and so miserable. And I was sore for like 2 weeks. I mean, my muscles just felt terrible, and I had so much chafing. It was ridiculous. Because I hadn't run I hadn't literally run, for more than a few miles in like 6 weeks. So
I remember every half marathon you did in graduate school, it was like worse weather than the last one.
Yeah, I had one good
really
when I
bad
first
luck.
started my faculty job. I had a really great half marathon weather experience and a really great time. I thought it was a great time. It's definitely my PR in Philly, and I haven't done a half marathon since. But that is okay. Okay, so I think everything is good now. So let's see if we can do this.
Hey, thanks, John. Collection of letters and numbers for following. John MCT123. Okay, we got chats back alive again. Alteric discourse. I was trying to figure out how to visualize. I'm not sure what this means. 3 series, infinite well, give 3 energy eigenvalues and 3 eigenstates. So I'm not sure I follow. So if you have an infinite well potential, that's going to have infinitely many energies and eigenstates. Can you clarify the question? And then in that infinite well case, you probably know. They're going to all look like standing waves, you know.
Yeah, there is, I honestly can't remember this or explain it off the top of my head. But there is some relationship between the number of bound states and like the depth of the well and the finite potential. I guess it's both depth and width of the well. I don't know.
All I know about the finite well potential in terms of this is there's always one bound state, no matter how small the barrier is.
Okay.
A three-well chain. So you have 3 finite wells strung together. I guess I don't think I've ever solved that problem. The potential is 3 wells. I guess if you set x equals 0 in the middle of the middle well, the potential is even. That means the ground state should be an even function, which I guess would look like occupation in each of the wells. I don't know. That's just speculating, because again, I've never solved this problem. All right, Jay, what's the status here?
We're writing our first unit test. Maybe before I do that, let's try. Sometimes I think unit tests are really high pressure.
I think any live coding exercise with an audience is high pressure.
I'm doing pretty good then, I think.
I asked a bunch of people, well, you have experience. I asked a bunch of people at this conference I was at last week if they wanted to come do this, and the consensus was like, that sounds hard.
It's okay. I like it.
Speaking of live audiences, hi, Lemon Bar 21.
Okay, first I'm just going to try out our functions in a little test script.
I'm great, Lemon Bar 21. How are you? I thought that was intentional. I'm doing well, just hanging out with my friend Jay, watching him write a unit test. What a way to spend a day.
Hey, are you drinking anything?
I have a mug of something. It's a mystery.
I have this stuff called space lettuce. It's really delicious.
Space lettuce?
Yeah. It's a double IPA from Monday Night Brewing in Atlanta.
That sounds great.
Mm-hmm.
I've never heard of Monday Night Brewing.
Having been sick for the last however many days, I have not had any alcohol in. I can't even remember how many days. A few. It feels like a long time. That doesn't sound good. That sounds like I drink too much. You know what I mean?
I'm not going to touch this one.
Yeah. Okay. What's our thing called? Thermal radiated power. It's there. What do we get?
Sorry, there's no attribute thermal radiated power.
Mm-hmm.
All this for nothing.
All this for nothing. Let's see what happens if... Can we do test? If cooling is in ARGs.
Lemon Bar 21, you got any questions for Jay Foley, professor of chemistry from William Patterson University, struggling to write some Python code? Okay, go for it.
I'm doing cooling. You should, okay, so you should have this stuff. Oh, as TMM driver has no, so there's many errors. Look at this. It's not good.
Okay. Jay, how are you on this fine morning, day, or night?
Oh, I'm doing good.
Fine like wine. That is a good question. It was easy to answer.
TMM driver object has no attribute black body spectrum. Okay, I think we can fix that.
Did you spell it wrong? I didn't have an underscore.
It might have had an underscore. Let's see. And maybe I need to, it's probably this thing I gotta compute. No, it's just, it doesn't have an underscore, but I have to compute it. It's not automatically computed. So
So as part of your unit test, you have to unit test that you calculate this correctly.
yeah.
Gotta be honest, I started with Python legit 4 days ago, so this looks absolutely insane. You know what, Lemon Bar, I'm not a Python person. I have no idea what's going on right now.
Takes 3 positional arguments before we're given. Okay.
I'm kind of lying. I just have never done any class stuff in Python, so the self dot drives me crazy.
How do you do it in C++? What's the...
What do you mean? It's a class. It's the same thing.
Places.
Oh, well, I mean, if you're inside a class function, you don't have to say self because it's you are in the class function. But if you can pass an instance of the class to another function with this.
Okay.
That's sometimes useful to do in callback library calls that have callback functions and want a piece of data, and so you can just pass the class itself as that data.
Thermal radiated power. Thermal radiated power.
I don't remember if I specified you'd be doing this in Python. I think I did.
Look at this. I have a number.
Is it the right number?
I doubt it, but that's okay. That's not
the code
I'm not expecting it to be
executed
the right now, or I'm not expecting it to be the right number yet because I'm not doing the same material. So let's make sure I'm doing the same material first. And then how do I do? Okay.
So I probably wasn't paying close enough attention. Where is this test coming from?
Yeah.
You have a right answer, or you just have...
I have a right answer. So the old version of WPTherml, and one of the things, this is while you're getting your power cord. I'm going to make a really simple multi-layer. It's only got one layer, and I'm giving it a static refractive index of 2.4 plus 0.2i for all wavelengths. And the reason why I'm doing that is because I'm not confident that all of the same refractive index data sets from our materials in the old version are the same as our new version.
So this radiative cooling function existed in the old version. That's what you're saying? Okay.
Yeah. It did. What we have
I'm sorry, radiative cooking.
Cooking, yes, yeah, yep. So let us do this. Test dot refractive index array.
So do both of you stream as a duo, or is it just one of you that stream with special guest appearance? Well, so this is my thing, super coding fun time with me, Eugene. But it's so lame when I do it by myself. And Jay has been kind enough to come on a few times and keep me company. I think this is your third time coming on.
Mm-hmm. Yeah.
And
it is my third time. Yeah, exactly.
I keep trying to convince, I guess I've streamed by myself maybe twice. With mixed success. And I keep trying to find other people who want to come on, but it seems a lot of people have a hang up about doing a live coding exercise with an audience, because it can be frustrating, especially while trying to have a conversation.
I think, yeah, this is, if you teach students coding, it feels almost no different than that. My humble opinion.
Yeah. Well, I mean, you have to get used to being stupid in front of other people. And then once you're used to that, it's no big deal. Not necessarily being stupid, but making mistakes.
Yes. And and also.
So now this is even weirder. So now you have a different class that's.
No, yeah, this is really unfortunate, because I didn't create a wrapper for all of these stupid functions in this this main driver. So it is a little ugly right now, but I think we're gonna get like an answer, and we can see if it's the right answer. I'm doing coolly. Too many indices. Uh-oh. Oh. Yeah, of course. That's the wrong array. Refractive.
You fool.
Yes. $40.445. How close is that to the other number? 40.445.
Oh, no way.
All right, we have to canonize this unit test now. Okay, so so here's my. I'm gonna put this. This is gonna be the most exciting part. It's 9:50, so I'll have a whole hour to spare.
If you're staying on till 11, yeah.
I probably will not. We're gonna get through all three of these unit tests. Then I'm gonna push this thing up to GitHub and create a pull request and ask my graduate students to check it out tomorrow. Okay, so test compute thermal radiative power.
So this stream is like a research productivity time machine.
Yeah, right.
Just launched you into the future. You're ready to go.
Totally has. This is really great. No, that's what I was trying to say earlier. It's like this has been on my research to-do list for a while. So I feel very good about this. So now I'm putting this into test_thermal.py. This holds all of the unit tests for the thermal functions. And once I get this written, I'm gonna spend just a few minutes talking about what is special about unit tests.
Do you have 16 slides on that too?
No, I don't. I'm just gonna I didn't prepare slides. Lucky for you, I did not prepare slides.
So I gave a talk last week at this quantum chemistry conference, and it was a completely new talk. It was all on polarotonic chemistry. So like Jay knows this. Photons and molecules strongly interacting. And I had like 100 slides, and I finished with 10 minutes left.
Wow.
I just go too fast, I guess.
We get our number. Okay, so before I talk too much about a unit test, every unit test is going to have at least one expected value, and then the value that you compute, and then you want to compare them. And you're going to compare them with an assert statement. So you're going to say assert, and I like NP is close.
It's close. I know that one.
Yeah. So then my expected value, my computed value, and then some threshold. I'm going to do 1 e to the minus 5.
45. Beyond machine precision.
45.
Is that enough? 45. Is that enough precision?
I think that's enough precision. I mean, this is in watts per meter squared. So this is 10 microwatts per meter squared. I think that's pretty good.
I always have a hard time with this coming from quantum chemistry. Like, you should get 12 decimal places if your code's correct. And then I remember working with Steven. Jay and I worked for the same guy as postdocs, and he was like happy with an order of magnitude. He was like, "Yeah, your code's working," and I had no idea if my code was actually working.
I passed. This is the one we just added. Compute solar radiated power. It passed.
Fantastic.
Okay, so what's a unit test? So let me. I'm gonna make this really big in my terminal. So we have. This is the main folder of our package in development, and it's going to be called WPTherml when we release it. But for placeholder, we're calling it WP spec dev. So if all of the code for WP spec dev sits in WP spec dev / WP spec dev, and then there's a subfolder called tests, and then tests we have a bunch of different Python files. They all start with test. So test_em is going to test all of the functions that are contained in the file em.py. There's a file called materials.py. All of the tests for those functions are in test_materials and so on. We just added our functions to thermal.py, so we added our unit test to test_thermal.py. And if I show you what this looks like, right, basically you have a bunch of functions in the unit test, and they all start with test, and then they all come with after test underscore and then the name of the function that they were trying to test. And basically each one of these test functions is going to set up a little calculation, get a result, and compare it to an expected result. And sometimes an expected result is just a number, and sometimes it's an array. And if it's an array, you can do, instead of is close, you can do something called all close or any close. And those are two different ways to compare arrays. Okay, so that's
please,
kind of
are any of these numbers correct? Is that
any
close?
Yeah, exactly. Any. So any close is kind of a weak test. We always do all close. But yeah, this is an important thing to do. And then once you have these test functions, you can in that folder in the main in the main, what do you call it, the root directory of your package, you can run those unit tests by typing pytest. And I type pytest minus v because it will actually give me verbose output.
Wow, you have a lot of tests.
Yes. And I think there's also a way to, I can't remember. There's a way to figure out how many, this happens automatically when we create a pull request. There's something else called code cov, and it tells you how many of your functions are covered by a unit test. And ideally you want 100%, and I think we have something like, oh yeah, there's a way to, whatever. I'll show you when I do the pull request. Okay, so here we go. All of our unit tests are passing so far. I've written 1 out of 3 unit tests. Let's do the other 2. Hopefully this will work.
Oh, look, there's 2 J's. Oh.
Okay, so I'm going to do the same thing for atmospheric, but I'm just going to copy this basically and paste it into the atmospheric radiated power and just change.
Sentimode, thanks for the follow.
Right, everything is going to be the same except for atmospheric radiated power. Compute. And then hopefully my arguments are the same.
How many tests were you making? 3? You've done
3.
1? This is still
yes.
The 1, or this is the second
No,
one?
this is the next one. I need a new value, but next one. So this is, by the way, is not a very good cooling structure because the radiative power is pretty small compared to the solar power that's absorbed. So this is warming coming from the sun. This is cooling that we're radiating. And this is also warming coming from the atmosphere. So at least we're bigger than the atmospheric absorbed power, but we're lower than the solar power. So that's not so good. Okay, but this is
so this would be good for radiative cooling at night.
Yeah, that's right.
Okay.
Or at least it would be tolerable for radiative cooling at night. It's just really not good for cooling during the day.
Does WPTherml, so all of these are layered structures, so you're doing transfer matrix equations or something?
We also have me theory in there now, and we're going to put in what's called generalized multi-particle me theory for multiple spherical particles.
So for anyone listening, these are all classical electrodynamics methods that are specific to certain structures, either layers or spheres.
Exactly. Atmospheric radiated power passed. Thermal radiated. Nope.
Oh, it took a long time and it failed.
Oh, it's missing argument. Okay.
Is that why it took so long? It was looking for the argument?
Maybe. I feel like something a little weird here.
Well, it's going so fast, I have no idea.
Thermal radiated power. Test computed atmospheric radiated power. There's another thing. Luminous efficiency. Good. There's another line there that
when you run PyTest, if the assert doesn't throw an error, that it just says it passed. That's all it's checking for.
Yeah. Oh yes, exactly. Thank you for asking that.
I'm asking for my own curiosity. I don't ever use PyTest. How big is your group these days, Jay?
My group is six students. Yeah, 6 students.
All master's students or master's and undergraduate?
I've got one undergrad who works on an educational project. And the remaining are master students.
John MCT123. Yes, there is a C++ analog for unit testing.
Hey, John. That's John. You know John.
Oh, this is John who visited FSU. Welcome, John. Yeah. So, yeah, you can write tests that throw exceptions when numbers don't match, and there's C-test. I never use C-test, but I assume it does something similar to PyTest, where if no exceptions are thrown, that means it passed. And so, like, the codes, Jay is a Python guy, I'm a C++ guy. The codes we develop, we have tests for them as well. Interestingly enough, the tests are run on the Python side, though. So we have a Python interface to C++ codes.
We're going to pass. Yes, we passed. Okay. Oh, no. Same thing. Atmospheric radiative power. Oh, missing one positional argument. Okay, let's check this out. Oh, duh. Okay, I know what's going on here, I think.
What is a positional argument? What does that mean?
That means so see that all the functions have arguments, right? I think a positional argument is just one of these things. So the first positional argument is this one. The last positional argument is this one, I think.
Gotcha. So there's in Python you can have arguments that aren't required. So I guess this is a required argument.
That's right. Okay, yeah, I was missing the atmospheric transmissivity spectrum for computing the atmospheric radiative power. That's very important. Now it's going to pass, I'm confident. But yeah, John and Jose are going to be done in like a few months, and then once they're done, I will have 4.
So I know John wants to go to graduate school. Is that Jose's intention as well?
I think Jose wants to get a job. And
that is respectable.
Yes, that is very respectable. Okay, so this failed because our number is different. Well, that's an interesting difference. It's actually a big difference. I'm going to go, you know what I'm going to do really quickly is I'm going to cheat and look at.
Is it off by a factor of pi?
No, not even close. This is the expected value, and this is the value we got from the calculation. So that's very different. Okay, let me see something here. Somewhere I've got here's the old WPTherml code. So atmospheric And that number is way too big to be correct. Like, there's no way. Okay, so
Okay, so I learned about VS Code tonight. I think I'm going to check this out. Jay, this is crazy. I've streamed for this outreach thing 2, 3, 4, 5 times, and you've joined 3.
Oh, I really am a friend of the pod.
Yeah, you really are.
Not of the pod. I got to get you on the podcast, Eugene.
I'm gonna be so boring on there, but sure. I'll happily join. You had Leah on, right? My colleague Leah Nienhaus.
Yes. Yeah, she did an awesome episode on photon upconversion.
Cool.
And perovskites. Yeah, it's very cool. Okay, what could be going wrong? So this is the function that's supposed to be returning the stuff.
Was it off by 2 pi?
No, not. Let's look one more time.
It's a joke. It was like off by a factor of 20,000.
Just a little factor of 20,000. Okay.
Was it off by? I'm out of jokes.
So we've got theta values. 1 over cosine of theta values. Atmospheric transmissivity.
Do you have any zeros in the, or pi over 2?
Oh, you know, I wonder if this is like a weird thing to do. That's kind of a weird thing to do. I'm going to do like NP1s, then atmospheric transmissivity. So this is an array of 1s minus instead of a single value 1. I mean, maybe that's the problem.
Finally, a thing about Python I don't like, and it doesn't make it seem useful.
You can just create an array of 1s in like 3 keystrokes, but you don't like that.
Well, I don't like that. What if this was the problem? We're losing one. Thanks for joining us, James Tuplets 2.
Oh, bye, James.
Good luck with your lecture tomorrow.
Oh, still bad. Same
number.
Same number. Okay, let's see. What can we do?
I'm sorry, how do you know the right answer? Because you have it from the old version?
Yeah, exactly. Okay, so so what happens if I just do print atmospheric? Is it really bad to begin with? Like test.atmospheric radiated cooling?
How do you print the cool shades emoji?
Oh, that happens somewhere. Okay, so look at this though. This number is not like that bad.
Yes.
That seems reasonable, actually. Okay, so I don't think it's the function itself. Somehow I'm just doing something wacky. The cool shades emoji, do you want to see where that comes?
Sure. Yeah.
So, where is it?
The smiling
So
face with
when you
sunglasses.
compute spectra, it says your spectra have been computed. And this is the fire emoji. This is after the thermal spectra.
Yeah, it was the one above that. It was right above that. It's a really long string. Smiling face with sunglasses.
Yeah. Your spectrum computed. That's it. Yeah. Okay, so I think the problem must be that this compute explicit angle spectrum. Let's go. Somehow I've probably messed up the order of these arguments, and that's probably what's going on.
The VS Code was supposed to help you do this.
I know, but it only if you're not careful, you can still mess up. Okay. Test thermal.
Halfway there.
Okay. Could that be it? Let's hope so. How many times do you save your files before you consider that you've actually saved it?
1?
How many times do you LaTeX, PDF LaTeX, BibTeX, PDF LaTeX before you are convinced that it's right?
3, but now I use Overleaf, so that never happens anymore.
Yeah, that's true. Okay, I am tired of this. That's not the right number. Okay, I'm going to try this. I'm going to try one more thing, and then we're just going to move on because nobody wants to really see this. Test atmospheric radiant power. Okay. Okay, simple thermal. Done that. Okay. Hey Eugene,
Yo.
do you know the band Big Thief?
Who?
Do you know the band Big Thief? Look at that.
I know Lori Berkner.
I don't know Lori Berkner. Who's Lori Berkner?
I'll send you 2 CDs. Lori Berkner regular music and Lori Berkner Christmas music.
Oh, nice.
It's for kids.
Okay. Well, that number is also not right, but it certainly isn't as big as...
Later, Alteric Discourse. Thank you for joining us. It looks like Jay fell asleep too.
Time to go. This is driving me crazy. But this looks more close.
I mean, the other number you printed out was 47. That also looked normal.
Yeah. No, it does look pretty normal. Hmm. Hmm. All right. I'm going to worry about this one later. Let's go to the solar one. Uh, anyway, Big Thief is great. They have a new album out. It's fantastic. It's really long.
Oh, right. Music.
Yeah.
I'm so old. I don't listen to new music.
You
Occasionally.
would like them.
Sorry?
You would like them even if you only like old music.
What does that even mean?
I don't know. They're just good. There was like a period of time when I think it's I'm not I shouldn't say this in public forum with people that probably pay more attention to this than I do, but there was a period of time when it looked like Bob Dylan was going to be canceled, but I think in the end he wasn't canceled. But I wanted to, at that point in time, I wanted to say that, because like there was a lot of people that were really salty about Bob Dylan being canceled. Like, how can I just stop listening to Bob Dylan? It's like, well, you could actually just listen to Adrienne Linker, who's the lead singer and songwriter of Big Thief, because like literally she's just as good as Bob Dylan as the songwriter, and but also has a better voice and is a better musician. So.
Is this what you talk about on your podcast?
No.
Because everybody who's still here, and we've dropped down to 3 now. Jay has a podcast, and I would love to come on it and talk about light matter interactions. That's what it's about. It's all about, right?
That is what it's all about. Exactly.
Gapert-Mayer gauge.
That's exactly right.
And it's with his grad school buddy, Dugan Hayes. And they had a radio show on University of Chicago radio that played at like 2 a.m.
Yes, we sure did. Oh,
so I'm assuming that this podcast is just a way to relive. Let's talk about
exactly
the
right.
weirdest music that we could play at 2 a.m.
Pretty much exactly right. I understand why my numbers are not working out.
What is the reason? Was the temperature wrong?
Probably the temperature was wrong, but also the wavelength range was way off. Okay, let's try this one more time.
Sentimode says that's a serious hot take, Jay. I think he's referring to, or they're referring to...
Adrienne Linker one.
Number one, I didn't know Bob Dylan was about to be canceled. Whatever canceled means.
Pass.
It's not going to pass, Jay.
Pass. No. It's so close now. That's looking, it's not a factor of 2, but it's
Is it a factor of pi over 2?
No, I don't think so. Oh, maybe it is. Who knows what? Let's see.
Sensimode, I'm glad that we have such spicy hot takes that could drag you away from your unit tests. Over 2.
2.
3 quarters of pi.
1.5. 1.5. Come on, that's it.
Is that it?
That is it. No, it's really close to it though. That's so strange. Okay, I'm not going to figure this out right now. Let's see if the solar works.
Say something else controversial. Don't say anything else.
Don't say, shut up. You know what? No, I'm just gonna try the next one. I'm not gonna try to get this right. I'm getting sleepy. That's what's going on.
What time do you normally get up?
What time do I normally get up?
Yeah.
Oh, 5.
Oh my God. You need to go to bed. Why do you get up so early?
Because June gets up at 6.
Why do you need to get up an hour before your child? That seems crazy.
So then Jessica and I can have coffee and talk to each other, because we will not be able to talk to each other again until June goes to bed.
What time does she go to bed?
8. And then, you know what time we go to bed?
8:15.
Basically.
Probably because you get up at 5.
Maybe we go to bed at 9 on a good day. I don't have too many other controversial takes, I don't think.
I think getting up at 5 when your kid gets up at 6 is a hot take in and of itself.
That's funny.
We don't set an alarm anymore. Because
Really?
I'm going to sleep as long as I can, and then my kids will wake me up.
That's amazing. What time do they normally wake you up?
Close to 7.
Okay. I remember you got mad at me for waking you up sending a.
You texted me in the morning, yes.
Yeah.
It's okay. Greg texts.
I also don't sleep with my phone. My phone goes downstairs. So I don't understand these problems from people.
Why do you leave your phone downstairs? Because you don't want people to text you while you're sleeping?
Well, number one, I also put it on do not disturb. But yeah, I don't want to be tempted to check email or check Slack or check Twitter or whatever.
Hot take.
I don't know. Do you find it easy to disconnect from all of these things?
No.
Like if you're tempted to look at them, or?
No.
Yeah, I don't either. It's kind of
slowly killing me.
Yeah, exactly. Okay. Expected solar radiative power. Let's get this number. Let's try this thing out. And what am I going to do with atmospheric radiative power?
Look, the test will pass now.
Yes. I'll fix that. I'll fix you good.
Okay, that one actually passed, right?
That one did actually pass.
Hey, that one passed.
Yeah, because
you removed the assert. I fixed it. Hey, nice. All right.
Solar radiative power passed. Okay. So what I'm going to do, because it's 10:30, I'm going to status. I think we made some good progress. Git commit -m added cooling functions. 2 of 3 passed. Unit tests. Fix atmospheric. Git push origin cooling. There it goes.
Woo!
And let's check out GitHub. This is the last thing I'm gonna do, because I think this is the most fun part. we would go here. Tooling has recent pushes less than a minute ago. Compare and pull request. And I'm going to say added functionality, radiative cooling, applications.
Wait, do you is this a template that you've added?
Yeah, this is a template. And I will try to find where that is. There's a, I don't know, there's a YAML file somewhere or something that does this.
Cool. Mine's blank. Whatever I do.
This is so like, yeah, let me finish this pull request, and then I'll talk a little bit about this GitHub repository, because it's got a lot of cool stuff in it, and all of it comes from Mulsi. So I'll say radiative power calculated cooling tests solar absorbed power tests. Question.
It's a good question.
Power. Okay, so then as soon as I create the pull request, it's going to start running these unit tests on different versions, using different versions of Python on different operating systems. And that's one of the things that our GitHub does. So I'll come back to that and we'll see if they pass. But yeah, okay, so in GitHub, pull request template.md, that's where that thing comes from.
Cool.
And then the workflows is where, this unit test running as soon as we do a pull request. That's where that happens. I'm trying to think of what else cool that comes. Yeah, so this code cov runs whenever we do a pull request too. And so this is telling us that 74% of our functions have unit tests. And this is telling us that all of the unit tests were passing last time we merged into main.
Cool.
Yeah. So this Mulsi cookie cutter, there's this thing called Mulsi cookie cutter, and I think you can just install it with Conda, and you get this, or you can just install it with Git. I can't remember. Whatever. It's on the software package best practices. There's like a link where you can do it, and you get this repository with all these cool files, and you can configure them the way that you want, and it's really nice.
Cool. Yeah, I put the link in the chat a long time ago.
Cool. All right. Now there's 4 of me, I guess.
That's it?
I think that's it. I think I'm done.
All right.
I would have had just enough time to.
And we can't play Punch Out?
You could play Punch Out, I guess.
I don't have Punch Out.
Oh. I still haven't gotten past Soda Popinski. Did you ever play that game?
Yeah, I was terrible at it.
That game is so much fun, but it's also very frustrating when you get stuck on a character. Yeah, I don't know what else to say.
I'm a Mario guy myself.
Yeah, Mario is also really hard. So I started trying to play Mario 2, and I found that very challenging.
Last time I was on Ken Hansen's Ask a Scientist, I beat Mario 2 in, I think, 15 minutes, something like that.
Oh, wow. That seems very impressive.
I think I could shave a couple minutes off. It was 220. I uploaded it to speedrun.com.
Okay.
It was 221st place.
Wow.
Out of probably less than 300 submissions.
I'm pretty sure. Oh, let me show you all one of the unit tests that passed.
Whoops. Cool. That's awesome.
Yes. This is one other thing that you can get really obsessed about on your iPhone. To check at night instead of going to sleep.
To check if your tests are passing.
Mm-hmm. Or, to check, has anybody reviewed my pull request yet?
From your own package?
It's been up here for 3 minutes. Yeah. So.
Sent mode, sure thing. Okay. Jay, are you done?
Yeah, I think I'm done.
Okay. All right. Well, thanks everybody who joined us. I don't know. We haven't done this in a while. I would like to start doing it more often, so stay tuned. Thanks for coming on, Jay. This was great.
Thanks for having me.
All right.
Yeah, I'll take more opportunities to just crank through some work.
It's I keep
John.
telling myself that's going to be an opportunity to do that, but like everything I want to do is just not conducive to fun times on the internet.
John and Fegan, I guess you can go review that pull request now. I'm just joking. Please don't do that tonight. You can do that another time.
Do it at 5 a.m. when every normal person
I'm gonna
wakes
get
up.
myself canceled as a toxic advisor if I'm caught on Twitch joking about. Don't.
On that note, Jay is requiring his students to review something at 11 o'clock, and he should be canceled.
Mm-hmm.
Okay. All right. Good night, everybody.
Good night.